let's try a little group activity here. Don't worry, I'm not going to make you hold hands. But they tell me this room accommodates 54 students, and apparently the chairs are supposed to be in 6 columns with 9 rows per column. So if you all can, I can see 1, 2, maybe some people out here are in the middle. I just want to get an idea for the quizzes. I want to see if we can still hold the quizzes on Fridays in classroom here, or I might have to go for the afternoon or evening quizzes. So if you all can try to move or position your chairs, the first row being right up here, um, and then let's see if we can get 9 people in a row. Um, so please go ahead, move yourself. Drag your chairs into position. I think the first row right here is good. All right. Yeah, I know. Right. Okay. So are we getting 9 students in a row here? 3, 4, 5, 6, 7, barely 8. Okay. All right. So I guess there might still be some room up there, but we'll see. What do you guys think? Is this too tight for a quiz? No? Yeah, if we have to go to a different room for the quiz, I think I'll ask for a bigger room. But uh, okay, I guess this gives me some idea. This fits 9, I think. Yep. So it might be a tight fit, but at least this gives me some idea about how well we might fit. All right, so I should have given you the handouts too for today. There's a couple of extra handouts from last time in case you were missing one. One of the handouts is still something that we will try to finish. Another thing that I'll say that maybe those people who come early to the class try to fill up that side of the room so that people who are coming just in time can sit somewhere closer to this row. All right, so we just continue off of the lecture that we were doing last time. Essentially, that was a review of basic topics from your 371, 270, and 297, mechanics of materials and statics and so on. And I think about where we had left things last time was we were doing this in-class activity, which technically I should have remembered to collect at the end of the lecture, but so be it. We'll do that a lot of times in the semester, and you won't miss anything. All right, so what we'll do, very quickly, recap of this example problem that we were doing, and then we'll move on. I've added a little something to this example from the lecture that we had from the last lecture. We went through the example of making sure it was determinate, number of unknowns and equations were equal, and we took a look at how to quickly draw shear force bending moment diagrams. If you want to take the long route, I have let's see, if you have I have included these 3 steps for each one of those 3 cuts to try to figure out an actual expression for the shear force and the bending moment at some point x in the beam, and then based on that you can pretty much draw the shear force bending moment diagram of these types of structures very easily, knowing the external reaction here is P over 2 goes up by P over 2, nothing in the middle, then out here is P downwards, so you drop by P, go back to the end, and go back up by P over 2. And integral of the shear force diagram is the bending moment diagram, so that's an easy way to draw these diagrams quickly. I did not uh, point out last time that the deflected shape would look something like this, but hopefully it's clear to you. One way to look at this structure is really that there is a cantilever beam out here in the left part, and the right two-thirds of the structure is really a simply supported beam with a roller at the left and a pin support that settles by a little bit. So it's a simply supported beam on the right two-thirds of the structure. That's why this kind of behaves like a simply supported beam here, and this left half is a cantilever beam with a tip load here. That's another way to kind of visualize what's happening in this structure. All right, so what I'll do now is continue with the handout that I gave you from last time. That was on stress and tractions. So now, overall, what we are doing really is we are talking about these types of problems. We are trying to see how we solve structural analysis problems in general. And the most important things that we'll cover over the next couple of lectures would be these four concepts. I told you that to solve structural analysis problems, you have to you rely upon four concepts: equilibrium, compatibility, material properties, and boundary conditions are basically formulating the whole problem. So these are the things that we'll go in sequence and try to understand where they really come from. First one is equilibrium, meaning, of course, in simple terms, it's just sum of forces equal to zero. But when you're dealing with deformable bodies, it is a little bit more complicated. So the way we deal with equilibrium for deformable bodies is through quantities like stress. And another quantity which you might not have heard of, traction. How many of you have heard of traction before? So it's very related to stress, nothing to be it's not very complicated. Traction is actually uh, very similar to pressure. What is pressure? Anyone? Pressure, well, yeah, in simple terms, it's force divided by area. It's a distributed force over an area, that's pressure. But the key property of pressure is that pressure, like hydrostatic pressure, water pressure, is always normal to the surface that it's acting on. Right? Traction, on the other hand, does not need to be normal. It can be at an angle. So if I have this surface, for example, if I push down perfectly vertically on this, then it's a pure pressure. And if I sort of stick my hand onto it and then also slide it, push it down and slide it in one direction, then I'm not applying a force that's perfectly normal to it. That's basically applying a distributed force at an angle on a surface area. That's essentially what traction is. So how are these things related? Uh, we basically we need to realize that um, when we are trying to solve problems like this, like any structure analysis problem, we are used to drawing these beams like lines. But really what is happening is there is a three-dimensional structure, underlying structure that is deforming. And if you take, for example, I pointed out last time that in order for a body to be in equilibrium, every sub body or every sub part of that body also needs to be in equilibrium, right? So no matter what part of that body I choose, what part of that beam I choose, it has to be in equilibrium. So for instance, if I draw the left half and the right half of the beam and draw their free body diagrams, which is essentially what I'm showing you here, um, for the original beam, which has a uniformly distributed load on top, reaction at the left end, reaction at the right end, then this piece by itself together with the reaction would be in equilibrium. This piece by itself together with the reaction would be in equilibrium. And what we would have at the cross section would be some distribution like this. Right? This is something that you should have seen before in mechanics of materials. Essentially, the compression and the tension regions of the cross section combine together to give us a bending moment at that cross section, right? These small arrows, these are really uh, these are what are fractions. These are forces per distributed area. Make sense? If we take a look at this cross section, there's a lot of distributed force over this cross section, at the top half being in compression, the bottom half being in tension, and this really is what is traction. Um, in in addition to this type of a compression tension distribution, we also have a distribution for shear. The distribution of the shear, which when we draw like a shear force distribution or shear force at some point x, what is really going on underneath inside the beam is that there are tractions, shear tractions that are pointing vertically down on the left, vertically up on the right, and their distribution across the cross section looks like this, quadratic. And if you have started looking at homework 1, which I hope you have, then in homework 1 part B, I have asked you exactly this. I have asked you to tell me that if the cross section of that beam looks like a rectangular section, 3-inch cross 4-inch, then what does the flexural stresses as a function of y look like? They should be linear. And what do the shear stresses as a function of y look like? They should be quadratic. Okay, so, and I've also uploaded a handout for those of you who may not completely recall those concepts on the web page. By the way, how many of you visited the class web page and taken a look at the lecture notes? I've also uploaded the lecture video from last time. I'll continue doing that. So if I'm going too fast or if something is not clear to you during the lecture, you can always go back and view the videos as well. All right, so this is a quick word about what stresses, are, what tractions are. Essentially, stresses are like internal forces. When I have this beam, if I apply a uniformly distributed load, it bends like this, and if I try to visualize a part of that beam in this final bent configuration, then at a particular cross section, the forces that would be acting, distributed forces that would be acting at that cross section, are made up of all of these tractions. Okay, so let's try to understand when we say things like axial force, shear force, or bending moment, where do they really come from? I just told you that tractions look something like this, like a complicated bunch of arrows, distributed forces that could be normal or that may be uh, pointing in a tangential shear direction. The sum of or the resultant of all of these forces is what are axial force, shear force, and bending moment. So with that in mind, let me first try to define axial force, the net axial force on a cross section. So let me ask you this. What would be the net axial force on a cross section like this for some distribution that looks like this? Some compression, equal amount of tension. Net axial force would be 0, right? Um, we we do get axial forces in frame members where there is actually some compression or some tension in the member, but under pure bending, where compression is equal to tension, we obviously don't have any axial forces. So the way that we define this axial force N for a beam section is basically, for example, here I'm drawing this small arrow, which is really the distributed force per area. That's the traction. So I'll call it T sub I, that vector, and uh, dot product with the I vector. Can anybody tell me what is this? This is the, for each one of these arrows is being denoted by this traction vector T sub I. If I take the dot product of any of these tractions, it could be perpendicular to the cross section, or it may not be perpendicular to the cross section. If I take a dot product of that vector with this I direction, the I unit vector, what would we get? A dot product of any vector with the I direction would be its component along that direction, right? It's the axial component. So all I'm trying to do when I take dot product of the traction with I is trying to find what is the axial component of that traction. Clearly, for a traction like this, if I have a traction like this does not have an axial component, right? So all I'm trying to do is to try to figure out what is the axial force by taking a component of the tractions on the cross section with the ith direction. And if I do that, that's basically T dot I integrated over the entire cross section, which I'll call just dA. And let's say the area of cross section is A here. So if I integrate that traction all over the cross section, that should be my axial force, right? Similarly, shear force, it would be the same traction, T sub I cross section, dot product with what now? Okay, dot product with J definitely. And since I'm looking at the left side body, and our convention for the left side body is that shear force pointing down is positive, then I'll take a dot product of this T with minus J to get a positive shear force. So dot product with minus J unit vector, and then integrated it again over the area dA, and that gives me the shear force. So in your homework one problem, part B, what I'm asking you to do is to try to find these tractions. These tractions, hopefully this is sounding familiar to you. Have you seen these types of distributions before? Bending and shear type distributions before? Maybe long back? Okay, so it's time to revisit some of that. But this is just to make sure that uh, we don't get lulled into thinking in these in simple terms like what is the shear force, axial force, and bending moment. These are not just some simple quantities. These are really stress resultants. These are the resultants of all of these types of distributed forces. When I have a beam like this, um, there's a lot of things going on at the cross section if you look at it closely. The whole point of this exercise is to try to make sure that you realize that how shear force, axial force, and bending moment come about. How about the bending moment? Let's take a look at the bending moment. I just said up there that compressive force and tensile force put together cause a bending moment at that cross section, right? So if I take one particular arrow here, let's say if I look at this cross section here, one particular arrow of those tractions looks like this. To calculate the bending moment, I would just use the definition of the moment of a force. What is the definition of a moment of a force? R cross F. Does that sound a bell? Ring a bell? So R cross F is the moment, is a three-dimensional moment of this traction at about this point. That's what this is, P cross Ti. That's R cross F. And I take a dot product of that three-dimensional moment in the K direction. K direction is out of the plane. Can anybody think of a reason why am I taking the dot product with the K direction? If I have a three-dimensional moment pointing in some three-dimensional direction, and if I only want to know what is the bending moment across this cross section, the bending moment across this cross section, according to my right hand rule, would be pointing in the K direction. Make sense? So that's why the three-dimensional moment, uh, I'm taking the dot product of the three-dimensional moment in the K direction. That would be the bending moment for this type of deformation. The reason that we do need to take the dot product is, for example, if I have a beam like this, and if I take this right or one end of the beam and another end of the beam and twist it, I won't twist it because it will break very easily. But if I twist it, then it is not, this beam is not under a pure bending moment. Right? It also has a torsional moment along with it. So um, all of those bending, torsion, shear, axial force, these are all encompassed in these types of fractions. And uh, the conventional quantities like shear force, axial force, bending moment that we are used to using in our structural analysis problems are actually stress resultants, which are obtained by integrating those fractions over the cross-section area. Um, um, so, um, so all this is still related to equilibrium. As I pointed out, if you for equilibrium, what you do need is that each and every sub part, each and every sub body of a structure has to be in equilibrium. So if I pick out a piece when I have this cantilever beam, if I try to isolate some small piece, some small cube of material out here, can you can you imagine that the all the six faces of that small cube of material would have some fractions acting on all of those six faces? Does it make sense? If I isolate some cube of material here, and if I try to draw the tractions on all of the six faces, or the distributed forces on all of the six faces, that might look something, some complicated distribution like that. It would have forces on all of the six faces um, for a cube of material inside a body. Not making sense? Um, all right, so let's try this again. All we are trying to do here is to try to understand where do these equilibrium conditions, where do these equilibrium equations come from. Um, we will express equilibrium equations in terms of axial force, shear force, and bending moment. But in order to understand where these things come from, we talked about free body diagrams of parts of the beam. Now, I think intuitively you should be able to see that if I take a piece of the body in any structure, that piece of the body may be in compression, maybe in tension, maybe in some complicated state of stress. And that complicated state of stress is depicted by these tractions, which in turn boils down to these quantities. These are really the stress components. How many of you remember from maybe mechanics of materials that the stress really is not just force divided by area. It's really 9 different components, right? Sigma xx, sigma yy, sigma zz, and all of the shear stresses. So hopefully that should uh, maybe bring back some picture of mechanics of materials. So indeed, stress really is like a 3x3 matrix of of stress components. And in 2D, we end up using only the first 4 xx, yy, and the shear stresses are the ones that we end up using in 2D. So I won't go into too much detail about all these different components, but then let's try to use um, these stress components to write out equilibrium of a body. Um, and hopefully, again, this is something that you should have seen before. Maybe not in these particular terms, but um, if I take a structure, any complicated structure, doesn't matter what structure it is. It could be a building, bridge, dam, or whatever, a chair you're sitting on, a table, or whatever. If I take a piece of a body, a very small piece of that body, that that possibly looks like this cube, and if I shrink that cube down to in the limit where each of the sides is tending to 0, then we can show that simple equations like this, sum of forces equal to 0 in x, y, and z, end up being these differential equations. These differential equations which are written the in terms of these stress components. Anybody seen these equations before? Again, this is from your either 270 or 231, which are mechanics of materials and structural mechanics classes. Um, and these really are the true equilibrium equations for deformable bodies. No matter what deformable body you have, these are the equations of equilibrium which end up translating from sum of forces in the x is 0 from y and z. If you do that for any point, these three equations, these three differential equations must be satisfied at each and every point of the body everywhere. Okay, so these really are the equilibrium equations for deformable bodies. Now let's look at something that you hopefully have seen before. Um, um, Equilibrium for beam structures, right? A simple beam structure like this, some distributed load acting on top. If I draw the free body diagram of a small piece or a small segment of that beam, that free body diagram might look something like this. On the left hand side, I have a shear force V, a bending moment M. On the right, I have V plus delta V and M plus delta M. There is this distributed force W delta X acting. And using this free body diagram, I should be able to write equations of equilibrium. I should be able to write sum of forces in the y direction is 0. I'm not too worried about x direction because clearly there is no, for beams we are not really too worried about axial forces. So how about sum of forces in the y direction? Um, can you If we sum up the forces in the y direction, we have V pointing up, V minus V plus delta V pointing down. What other y forces do we have here? Omega delta X, and that's in the negative direction. So we have minus W delta X, and clearly no other no other force. So if I take this, maybe I should, V and V cancel off, and I can rewrite this as W is equal to minus delta V over delta X, and in the limit, so maybe I'll write that here, with limit delta X tending to 0, I would get that equal to d minus dv dx, right? This is hopefully something that you've seen before. And similarly for equation of equilibrium, equation of equilibrium for the moments about the point C prime, about this point. Maybe take 30 seconds and write down that equation, see what you get, and then let me know. Sum of moments about this point. All right, anybody want to give me the first term? How about this moment? Is this moment positive or negative about point C? Negative, all right, so we'll write that as minus M. This M plus delta M is positive, so M plus delta M. And what other moments do I need to account for? Okay, that's negative V times delta X. What else? Okay, so that's positive or negative? Okay, positive W delta X, that's the force, times the moment arm, which is delta X over 2. And all of that there's clearly no other moments. I have been counted for these two and that force. The moment you do this force will obviously be zero, and we also counted that. So if we apply the same logic that we did on the shear forces, M and M cancel off. Um, and um, this term, this term, the W term, which has two delta x's in there, delta x times delta x squared, will drop off to zero as delta x uh, tends to zero. Therefore, sorry. Therefore, what we should get is that V is equal to limit delta x tending to 0 of delta m over delta x, and that's simply dm dx. That's basically where we get the relationship that shear force diagram is looks like the derivative of the bending moment diagram, right? So essentially, these are equilibrium equations for beams. Where did they come from? They came from very basic concepts like sum of forces in the y direction and sum of moments are zero. Where do these come from? They come from deformable form equations for deformable objects that look like these complicated differential equations. But once again, we are not going to get into these complicated differential equations. We do need to have to be aware of where these equations are coming from. So that's the first principle of structure analysis that we were talking about, equilibrium. For beam equilibriums, we are going to rely upon these equations. The applied distributed load is the negative of the derivative of shear force diagram. The applied or the shear force at a cross section is equal to the derivative of the bending moment at that cross section. These are just equilibrium equations. All right, so let's talk about something that's that's related to deformation. Compatibility is related to deformation. Like I told you last time, when bodies deform, in their deformed configurations, each and every small piece of that body has to fit together with the rest of the body. That's the statement of compatibility. So deformation is what we're going to talk about now, and the most uh, the way we measure deformation is through strains. So here is a simple example of a structure. It This is a one-dimensional bar, but with a varying cross section. If I have a one-dimensional bar like this with a uniform cross section, then if I apply some force at the right end, some force at the left end, that would be a uniform tensile force throughout the cross section, right? And it would be under a uniform state of stress throughout the length of the bar, and the the extension of the bar would also be pretty much uniform all along the length of the bar. So if I say that if under a force F, the bar extends by an amount delta L, then you can take delta L, the change in length divided by the original length, and that's what we normally use as a measure of strain, right? But things are not so simple if you have something that is deformable or of a varying cross section. So, for example, in this, if I have a bar with a varying cross section, the amount of extension near the ends where the bar is thinner would be more. That makes sense? The amount of extension near the regions where the bar is thinner would be more. The amount of extension in the middle of the bar where it is actually thicker will be less. So when I ask you what is the strain of this bar, say for example, originally the bar was this black outline. When I applied the forces in red, it took the shape of this blue outline. So when I ask you what is the strain of this bar, you should ask me back at what point. Strain is not something strain is not an average value. What when we say that strain is delta L over L, that's an average measure of strain. It does not work well for bodies that are not of uniform cross section. So the true definition of strain in one dimensions is really that the strain is the derivative of displacement. So if if you take a piece of that material in the undeformed and the deformed configurations, you can figure out that the strain at this location would be given by the derivative of the displacement at that location. And this is true even for three-dimensional objects. It's just the fact that the derivatives become much more complicated in three dimensions. So I won't go into detail about all of that. But technically, when we talk about strain or a deformation of a body, it really is a 3 cross 3 matrix, just like that uh, stress stress matrix. So um, but the whole point here is our simple definition of change in length divided by original length is an average measure of strain. And to get a point-wise measure or a pinpoint measure, we need to take derivatives of displacement. And how does that translate to beams? Let's talk about that. Um, um, in beams, what we really uh, what we really rely upon is a fundamental hypothesis of beams. What is that hypothesis? Right? Plane sections remain plane. That's the fundamental hypothesis of beam theory. And actually, it's much stronger. Not only do plane sections remain plane before and after deformation, it's actually cross sections of the beam remain rigid. Rigid cross sections remain rigid before and after deformation. So if you can see this beam, there is a center line right across the longitude here, and there's a bunch of these vertical lines that denote cross sections all along the length of the beam, right? And as I deform this beam, even to pretty large deformations, hopefully you can kind of see that all these vertical lines remain straight. They they go like this, but they remain straight. They don't curve out of plane, or they don't become the vertical lines don't become curved, right? So this is a fundamental hypothesis. This is an assumption behind the beam theory that plane sections remain plane, or actually rigid cross sections remain rigid before and after deformation. So the best way to really visualize a beam is to think of the centroid line as some sort of a flexible string, and there are infinitely many cross sections, rigid plates, rigid cross sections attached to uh, to that to that string of centroids. And those cross sections, adjacent cross sections, can bend with respect to each other. They can slide with respect to each other, but they cannot warp out of plane. Okay, so any deformation of a beam has to be in terms of the deformation of the centroid line and of and the movement of all of these infinitely many cross sections. That's what really beam theory relies upon. So, as I was just telling you, if you think of those of any two adjacent cross sections, there are these three modes in which beams deform. One is a pure bending mode. Okay. Um, let's see. I can probably use this book. Uh, if you think of this top line of the pure bending mode of deformation, think of uh, any two adjacent cross sections in this beam. These two adjacent cross sections. When I apply some moment at the ends, those two cross sections are bending toward each other. Make sense? And um, those cross sections, when they bend towards each other, let's say this face is one cross section, this face is another cross section. The bending deformation at between two adjacent cross sections looks something like this. This type of a deformation mode of two adjacent cross sections is a bending deformation. The second one is a pure shear. where these two faces move with respect to each other. If one goes down, one goes up, that's a pure shear deformation of a beam. Now, normally in all of the structural analysis that you might have seen in 371, we neglect shear deformation. Why do we neglect shear deformation? The shear deformation indeed is very small under some circumstances. Under what circumstances? Small loading, but more importantly, that the structure itself has to be slender. The beam or the column has to be slender. What is slender? That the area of cross section or the dimensions of the cross section have to be much smaller in comparison to the length of the member. So if it is slender, then there is a lot of deformation. But most of this deformation is coming from bending. If you look at any two adjacent cross sections, those adjacent cross sections are doing something like this here, this here, this here, and so on. So almost all of the deformation for a slender beam is through bending. There is shear deformation, but very negligible. On the other hand, if I flip the beam over, now it becomes a deep beam. If I try to apply the same moment here, the, the deformation is not too much. And in such cases, shear deformation does become important. In such cases, for deep beams, you cannot neglect shear deformation. So only for slender structures, the deformations are so big that the shear deformation is negligible in comparison to the bending deformation. For deep beams, shear deformation is not negligible in general in comparison to bending deformations. So, and lastly, of course, we have purely axial deformation. If I take the beam and compress it, it would actually shrink in length, and that's the third mode of deformation. Because these would be the only three modes that are possible. Why? Because the cross sections are rigid, right? So with these assumptions, we people have formulated these two different types of theories. One that allows for shear deformation, and one that does not allow for shear deformation. It allows only for pure bending. And those two theories are called the Timoshenko beam theory, which does allow for bending, shear, and axial, all three modes of deformation, and the Bernoulli-Euler beam theory, which is the one that you have been using in your structural analysis courses, structural mechanics courses, and even in this course, we are going to rely on this Bernoulli-Euler beam theory, where we assume that there is no, or that the beam is rigid in shear, that there is no shear deformation. The only deformation that we'll be considering would be pure bending deformation. Okay. Any question on any of these conceptual things? So I'm just trying to set the stage of, or set up the big picture of where structural analysis fits. When we go on and do shear force and bending moment diagrams for beams, what does that really mean? What is shear force? What is bending moment? They come from tractions. And when we try to solve for like different deflections of beams under certain types of loadings, those deflections come from where? These are some basic things that we are just talking about now. So so with this, some more basic relationships about the strains in Bernoulli-Euler beam theory. So as I said, we'll be focusing on Bernoulli-Euler beam theory, where we assume that the strain deformation is negligible. And in this case, what we do really is, for beams, the fundamental quantity of strain is really curvature. How do we define curvature? In this manner. So let's say I have some beam out here. I've applied some loading to that beam, and under that loading, it has deformed to some different type of some sort of a shape. Okay. So if I look at some segment of that beam, any random pick at any random segment of that beam. If there is no shear deformation, if the only deformation is bending, then the only thing that can happen is two adjacent cross sections going like that, right? Under those circumstances, you can easily fit the center line of the beam as a part of the circumference of what is called the osculating circle. Right? If you go along the length of the beam, it might be a different osculating circle at different points. If I have a lot of bending, the size of the osculating circle would be very small, right? If I have, let's say I have a this type of a end moment applied at both ends, and if I look at potentially the oscillating circle for this amount of bending, that circle might be very big. If I apply more moment without breaking the beam, um, then the size of the oscillating circle shrinks. And um, it's not necessary that it has to be the same osculating circle everywhere along the beam. In fact, of course, at different locations of the beam, you may have different oscillating circles. But the reason that we are talking about these oscillating circles is because that helps us in quantifying something called the radius of curvature. The radius of curvature, which I'm denoting with rho here, it can be shown that curvature, which is really d theta over dx. What is theta? That's the angle, this angle that a cross section makes with the horizontal. That's theta. So how does that angle, if you look at all of these cross sections, how does that angle change along the length of the beam? D theta over dx, that's the curvature. That's the fundamental strain quantity for beam theory. And it is equal to 1 over the radius of curvature. And you can also show through um, through this that through this definition that if I have two if I go to a certain location of the beam, if I have two rigid cross sections, and after deformation they point like that, then at the center line or the neutral axis of the beam, the strain is zero. Right? No compression, no tension, so strain is zero. But as I go up as a distance y, then the strain at a distance y is given by that distance y divided by the radius of curvature. Can anybody tell me where does this minus sign come from? Or why is there a minus sign? If I'm at the centroid line, if I go above the above the centroid line or above the neutral axis, strains are positive or negative? Negative, compressive strains, right? So that's why this is minus y over rho. That's uh, that's the strain at some distance y. Since 1 over rho is the definition of curvature, I'm not going through the derivation of all this potential. Well, I'm assuming that you've seen these derivations before, and if not, then I've already posted the handout um, on the on the class web page. You can take a look at that to refresh your concepts. And essentially, we see that this is where the logic comes from. That the variation of the strain across the cross section is linear. If the variation of the strain is linear, variation of the stress ends up being linear, right? For linear elastic materials. Um, and finally, so we've talked about equilibrium, we've talked about strain or deformation, and finally, material behavior. Again, I'm not going to go into too much detail about the three-dimensional material behavior, but as you can expect, if I have a if I have some cylindrical piece of material that's shown in this black outline, I apply some forces, it goes out to say this blue outline, then the amount of extension that I have will depend upon the material property. Two different materials that were originally of this black outline will go to two different lengths under the same applied force. And for linear elastic materials, we get that amount of extension using the Young's modulus. So hopefully you all remember that this simple relationship, that stress would be force divided by area. If we take the average strain, that's delta L over original length, which combined both together with this formula for the Hooke's law, stress is equal to Young's modulus times strain, you immediately get that change in length would be F times original length L divided by area of cross section and Young's modulus, right? Um, so this is a very simple relationship for material properties. But like I said, in 3 dimensions, it's much more complicated. And again, we won't talk about that in too much detail. But for beams specifically, what does that material relationship amount to? It amounts to the relationship between the beam measure of strain, which is curvature, and the beam measure of stress resultant, which is bending moment. So M is related to curvature through EI, that's the bending stiffness. EI is the bending stiffness, right? And by relating the strain to the stresses and calculating the bending moment through that, you can easily show that uh, bending moment at a cross section is equal to EI times curvature, where and that's another reason why curvature is sometimes calculated as M over EI. So if you draw the bending moment diagram of a beam, and I ask you for the curvature diagram, all you need to do is to divide by EI, right? All right, so I think I've given you a lot of things to digest in one day, but this is all technically supposed to be review. And if these are things that are not making sense immediately, please go back, review the lecture, and review the handouts that I've posted on the Blackboard webpage. And don't forget, on Friday by 5 p.m., your homework one, part one, should be uploaded to Blackboard. If you have any questions, Dr. Liu will be holding her office hours right after this class right now, and I'll be holding my office hours tomorrow from 3 to 5. All right, so see you all on Friday. Sure.